Now that we have seen some of the ways in which an object can change its velocity, we want to define this property in more detail. So at the end of this lesson, you should be able to define acceleration, determine the magnitude and direction of an acceleration, and relate an object's acceleration to its change in velocity. So these are the summary questions you will need to have in your notes. So let's review a little bit. Remember that displacement is an object's change in position, and it is not necessarily the total distance that the object travels. Displacement is found by taking the final position minus the initial position. Sometimes this gives us a negative number, and that just indicates which direction the object is traveling because displacement is a vector quantity. We will typically measure displacement in meters, but sometimes centimeters is more appropriate. Velocity is the rate at which the displacement changes. So we are looking at how the object's position changes over time. We can find velocity by taking the displacement divided by the time. This gives us a label of meters per second, and since velocity is derived from displacement, which is a vector quantity, velocity is also a vector quantity. So now we come to acceleration. The graphs that we have looked at in our lab and our second position time graph worksheet were not linear. Remember, the slope of a position time graph indicates the velocity. So look at the slope between these 2 points at the beginning of this graph. How would you describe it? It's not too steep. The position of the object has not changed a whole lot. Here we would say that the car is moving with a fairly slow velocity. But what about these next 2 points? What is different here? Looking at the bracket, it appears that the object has changed position more during this time period than it did in the first time period we looked at. So what about the slope? The slope is steeper in the second time period than it is in the first. This means that the velocity during that time is more than it was in the first. So what happens in a third time period? Again, the slope is more than it was before, and the car is covering a larger distance than it was. And this last one, the same pattern emerges. The car covers more distance in that time period than it did in any of the previous ones. This results in a steeper slope on that portion of the graph. And so if we look at the different slopes as we go along, this tells us that the velocity of our car is changing as time goes on. Every time period, the car covers a greater distance than it did in the time period before. And when an object changes its velocity, we call that an acceleration. So what are the ways in which an object can change its velocity? Well, we just looked at how our car was speeding up as it went along. The opposite could be true as well. What happens when you push the car up the ramp? The distance that the car covers every time period in that case was less than as it went up. So we could have a velocity that is getting smaller. That would still be a change in velocity, so we would also call that an acceleration. Can you think of a third? So a third situation would be the object changing direction, and that would in fact be accelerating. So acceleration is defined as the rate an object changes its velocity. So it is a rate of a rate, and we are getting dangerously close to calculus here, but we won't go there. To find acceleration mathematically, we would take the change in velocity and divide it by the time. We have seen that delta before. We were talking about it in terms of a change in position before, and we called it delta x. Here it's paired with a v, which stands for velocity in our equation. So any guesses on how we would solve for delta v? We need to take the final velocity and subtract the initial velocity. So delta v is the change in velocity. T is the time. Divide those two to find the acceleration, which we abbreviate as a. But how do we label acceleration? Let's look at how this would work out. Acceleration is the change in velocity divided by the change in time. Velocity is labeled as meters per second, and time is labeled as seconds. This gives us our first really weird looking label of meters per second per second. A lot of times we'll see it written as meters per second squared. One last thing to keep in mind, acceleration is a vector quantity, so we will need to indicate whether it is positive or negative. This gets a little bit complicated because the positive does not necessarily mean the object is speeding up, and the negative does not necessarily mean that the object is slowing down. We will look at some velocity time graphs later on to see how all this plays out. So let's say we have a sprinter that is starting from rest and reaches a speed of 12 meters per second in 4.25 seconds. Find his acceleration. So what do we know in our problem? So when we talk about finding the knowns and the unknowns, this is what I mean. VF would be the final velocity. So he reached a speed of 12 meters per second. So our final velocity is 12 meters per second. VI is going to be the initial velocity. We started out at rest, so our initial velocity is 0 meters per second. T is time. We also know that. We know that he took 4.25 seconds to go from rest to 12 meters per second. We are trying to find the acceleration. So the acceleration is our unknown. So we know the final velocity, we know the initial velocity, we know the time, and we are looking for the acceleration. So acceleration we find by taking delta V divided by t. So we need to know what the change in velocity is and divide it by the time. So do we know the change in velocity? Well, not directly, but can we find it? Remember, change in velocity is going to be the final minus the initial velocity. And we do know that. We know that we had a velocity of 12 meters per second as our final velocity. And we're just going to assume that it was positive. It doesn't really give us a direction. So we're just going to say that was in the positive direction. So positive 12 meters per second minus the initial velocity of 0 meters per second, which is at rest. And we find that we have a change in velocity of positive 12 meters per second. So now that we have our delta V, we can go back to our acceleration equation and plug that in. So we have delta V divided by t. When we take our positive 12 meters per second, we're going to divide it by 4.25 seconds, and we're going to get positive 2.823529412 meters per second per second. Now don't even consider writing down every single one of those numbers. We talked about the rounding in Unit 1. If we go back and we look at our problem, we have 12 and we have 4.25. So we either want 2 or 3 numbers in our rounded answer. So we're going to take our number and we're going to round it to positive 2.8 meters per second per second. Let's look at another one. The sprinter crosses the finish line with a velocity of 12 meters per second. It takes him 2.7 seconds to come to a stop. Find his acceleration. So remember, acceleration is any change in velocity. So even though we're slowing down, we still call that an acceleration. So what do we know in this problem? We come to a stop, so our final velocity is 0 meters per second. We started out with a velocity of 12 meters per second, and we're going to assume that's positive again. And we have a time of 2.7 for all of this to happen. So our unknown is the acceleration. So again, we're trying to find acceleration. And again, we need to know delta V. So delta V, we're going to take the final minus the initial. Our final velocity was 0. And we are going to subtract our initial velocity, which was 12. So we have a negative change in velocity of 12 meters per second. So now we're going to take that negative 12 meters per second and we're going to divide it by our time, which is 2.7, and get a whole lot of 4s. Now again, how are we going to round this? We're going to round it to 2 numbers. So we're going to have an acceleration of negative 4.4 meters per second per second. So, can you define acceleration? Can you determine the magnitude and direction of an acceleration? And can you relate an object's acceleration to its change in velocity?